For the first application, I'll tell you about some of my own work on recipe recommendations, and this is joint work with my PhD student Edwin Tang and a collaborator, Yuru Lin, who works with David Lazar, whose name you've encountered before at Northeastern and at Harvard. So what we were interested in is whether, if one were to construct networks out of ingredients based on co-occurrence initially in recipes, later we also looked at substitutes, whether one could actually predict which recipe is better, right? I had approached this as someone who's not a very good cook at all. And I thought, well, I've solved so many other problems in life using data. Maybe I can solve my cooking problem by doing a bit of data analysis. And the cooking problem is basically this. If you have an expert cook, they can eyeball a recipe and just sort of tell, okay, this is going to be good or this isn't. Or they can know that, you can tweak the recipe and in which ways you can tweak it that would improve without, harming the basic substance of the food. And I just didn't know things like that. So I said, let's see if we can answer this question with data. And so the data set we gathered were over 40,000 recipes from the site allrecipes.com. And we discovered then a rich additional data set, which were nearly 2 million reviews of the recipes, which then included text as well. And what we wanted to know is what patterns emerge out of this aggregated knowledge, and how specifically can ingredient networks be used to predict which recipe is good. So out of all this data, we extracted the cooking methods. That is, are you going to boil it? Are you going to grill it? Are you going to chop it? The ingredients and what ingredients are together in the original recipe and what modifications are suggested in the reviews. And then we wanted to finally do a prediction. If we have a recipe for Grandma's Swedish meatballs, and we have another one that's the Amazing Swedish Meatball, and they have most of the same ingredients, but not quite. And maybe the cooking method's a little bit different. Can we use network analysis to actually predict which one's going to be better? So on the way, we kind of did a little bit of exploratory data analysis, not necessarily having to do with networks. So for example, we found that cooking methods differ by region. So you had the Northeast and the South more likely to fry their foods. These are regions of the United States. Grilling was more popular in the mountain and West Coast regions, for example. So we kind of had a sense, okay, there's some encoding of real-world phenomena in this aggregate data set. But what we were more interested in was, how can we apply network analysis to this? So we're wondering whether there are some combinations of ingredients that might, and this is just hypothetical, maybe bananas and blueberries go well together, but apples and corn not as well. So for the complement network, what we did was we constructed edges using the pointwise mutual information, which is just the log of the probability that the ingredients occur together divided by a product of the individual probabilities that a particular ingredient occurs in a recipe. And so, as you might imagine, the numerator is higher for ingredients that tend to occur together more than they occur apart. And you already saw this network in your assignment, and there were basically 3 main communities of sweet, savory, and mixed drinks. And depending on how you threshold and modularity and so on, you can find some additional communities in there. But we also wanted to know, what kinds of networks can we extract out of the reviews, and even before that, are the reviews tweaking, say, the quantity? So instead of 2 eggs, maybe you want to put 3, or maybe just 1, and maybe you want to add orange juice for some reason, or not, or strawberries, or who knows, right? There are all sorts of things that can happen when people review recipes, and this is kind of an interesting thing, which is that right around a rating of 4 out of 5, which means the person likes it, you see the most suggested modifications. This was good, but I would add this, or I would subtract that, or more of this, or less of that, etc. And this is less common for those recipes that get, kind of a perfect 5-star rating, or ones that people don't like. If it's beyond repair, they don't really bother to suggest these modifications. And yeah, so that's the main thing. And then you can look for individual ingredients, how many times are they increased, and you'll see things like garlic being way up, more garlic good, but maybe, white sugar, butter, the kinds of things that get decreased more than they get increased, potentially for health reasons. And in general, we can see some additional patterns. For example, ingredients that occur in a lot of recipes, meaning they're pretty essential, are less likely to be deleted. That is, people are less likely to take them out, and they're less likely to be added. I mean, probably they're so common that if they belonged in the recipe, they would have been included already, and they're also less likely to be increased. Now let's look at specifically the parts that we're going to build the network out of, and that is, we looked for patterns that said something like, I replace the butter with sour cream. So replace A with B, substitute B for A, B instead of A. And we had these edge weights, which was the probability that B is going to be suggested every time A was mentioned as being substituted with something else in a comment. And this, again, is a network that I think you've worked, or at least I've shown it to you in lecture before. So if we take the substitution network, already just laying it out, we can see pretty clear communities, and then we can apply community finding to actually have a network of different communities, which then we can look within each community and find, hey, these are the common substitutions for milk, these are the common substitutions for cinnamon. And they tend to make sense. Okay, so these communities, yes, they make sense, but do these substitutions actually encode users' preference? And for this, we constructed another kind of network, which we called a preference network. And that is, if you have two recipes that overlap in ingredients somewhat, but this one has one ingredient extra, or it has a different ingredient than this other one. So for example, one has ketchup and cheese and the other one just has pickle, and one gets a higher rating than another, you create these pairwise preferences, ketchup to pickle, cheese to pickle, for example, and you aggregate this over all the recipe pairs with sufficient overlap to see whether in general there's a preference of one ingredient over another. And what you end up seeing is that there is a correlation between the substitutions that are suggested in the comments and the differences in ratings of recipes that overlap in ingredients, except, you would get one recipe out of another if you just did that substitution. And so we have a very high correlation, which tells us that these networks encode user preferences. So let's see if we can predict, given two different related dishes that are somewhat different, can we predict which one is going to get the higher rating? And so we're going to use a baseline, which is just the cooking method, the preparation time, the number of servings you get. We're going to use just the raw ingredient list. So the 1,000 most popular ingredients, we get like a little prediction coefficient for each one of them. So maybe having chocolate makes the recipe better, and actually there's very little signal in that, just having an ingredient or not. Then nutrition information, and then we're going to include our ingredient networks, and finally we're going to combine everything. So for the prediction task, we gathered a bunch of pairs of recipes that were related enough that you could really compare them. So you weren't comparing pizza with a recipe for ice cream. You were comparing, say, two beef dishes that, two stir-fry beef dishes. And we wanted to be able to really tell this one is better than another one. And the way that we did this was we looked for recipe pairs where the same people rated both recipes and tended to prefer one over the other. So we had a ranking. And then we had, for each pair, we saw how well could we predict. If we were just guessing at random, we would be right 50% of the time, right? Because one of the recipes is going to be better. So we'd like to know, are we going to do even better than that? And we tried various machine learning techniques. The gradient boosting tree was the one that worked the best. And we saw an improvement over the baseline, which was about 72% correct, to about 78, 79%, and especially the ingredient networks gave us a lot of predictive power in figuring out which recipe is better. You can also delve down into the individual features to see which ones contribute more towards the prediction. And the single individual features actually had, the first three had to do with the cooking effort and nutrition, but pretty soon thereafter you see the ingredient network features playing a role as well. Looking within the network features, you can see that the substitution network actually counts the most. This is, I would substitute applesauce for oil. Just the raw co-occurrence and the complement are also important and in a sense complementary to the substitution network. You can further perform a dimensionality reduction and find which ingredients are grouped together under a common feature. And you see that, for example, this dimension here then contains Splenda, which is a sugar substitute, olive oil, applesauce, honey, butter. So it seems to have the sugars and fats, although in general these dimensions are kind of abstract, but it's still nice to see which, once you collapse the network, which ingredients end up being placed together. So just to conclude, you can have fun by creating a network out of something that normally maybe is not considered a network, right? Recipes are just lists of ingredients, but you get to decide, what brings different ingredients together? Is it that they co-occur in the same recipe? Is it that they co-occur more often than what would be expected? Is it that one is recommended as a substitute for another often? And you can then construct all these networks, and then a fun thing to do is actually to see whether you can predict something about the world using the information of how this network is structured. And this is exactly what we did with recipes. We showed that you can predict which is a better recipe based on ingredient networks.